Whether my screen is visible?
Yes, sir.
Okay, thank you. So today we are going to start a new module, what is called radial basis function networks. Now, so before that, we have to understand that what is this RBFN and in short, what we normally call, and why it is required as first of all, and what's the logical connection with the MLP. So we'll try to answer all these questions. And in the due course of time, we'll try to understand the basic principles of RBFN working and how it is better than other. So, so far in the basically in MLP, we have seen that there is a multi-layer perceptron. We have seen that MLP also is a supervised learning process. So supervised training of a neural network can be done by in more than one way. So MLP was one of the way using it means backpropagation was one of the technique using which you can train a network in a supervised fashion. And the way MLP uses this learning system, what is called stochastic approximation, basically. And I'll let you know what do you mean by stochastic approximation because it's what using an iterative approach. And so this is stochastic approximation of learning is one of the way. Another is curve fitting. So this radial basic function networks, which we in short we call it RBFN, is another technique which that is also used for the supervised training of neural network. But the approach it uses is what is called curve fitting. It does not use the concept of stochastic approximation. It uses the concept of curve fitting. Then the question comes, do I really need this? And if MLP was doing a good job, why should I go for this? So this answer you will only come to know for the due course of time once we complete some portion of this. Probably you'll be able to realize that why it is better than MLP in certain situation. Okay. So before we jump upon other part of it, and to understand the nitty-gritty of this topic, we need to understand some definition, basically two majorly. When I said this MLP, the training or the learning of the function or the model is nothing but using a concept called stochastic approximation. So what is this stochastic approximation method is all about? So as you can see here, it says that its methods are, so stochastic approximation methods are a family of iterative optimization algorithms that attempts to find zeros or extrema of function which cannot be computed directly but only estimated via noisy observation. So this is exactly what we are doing in the supervised training of MLP or the network itself. In MLP, what we have is a family of iterative optimization algorithms. So here we are going for this iterative process. So it's not family, but one. And we use this concept of backpropagation. We use every now and then to find the zeros or the extrema. So basically the derivation of the backpropagation is itself. At that time we said that it is a gradient should be zero or the minimal. And based on that, we derive those equation for change in synaptic waves, that is delta Wig is so and so, that is eta times delta J into Yi that we have seen. So basically it's directly make use of this concept. So that's why we call it a stochastic approximation approach, which MLP uses inherently. Now there is another approach, what is called curve fitting. So you know that curve fitting you would done probably in the first year of mathematics as well. So it's the process of basically curve fitting in the process of constructing a curve or mathematical function that has the best fit to a series of data points, possibly subject to constraints. Some constraint may be that. Curve fitting can involve either interpolation where an exact fit of the data is required or smoothing in which a smooth function is constructed that approximately fits the data. That is also possible. Okay. So the subject matter of this particular module, that is RBFN, it make use of this concept of curve fitting, and we'll see how. So particularly it makes use of this interpolation technique. And interpolation technique again something which you have studied during our first year of mathematics. So as I mentioned, this MLP, of course, supervised training of neural network is not the, it cannot be done in only one way. Multiple ways are there. MLP is one approach. So in MLP, what we did, you applied the recursive technique of stochastic approximation. That is, we keep on applying backpropagation and design of neural networks as a curve fitting approximation. Problems when you go for high dimensional space, we use something called radial basis function. So I'll explain what do you mean by radial function and all those things. Then we have the curve fitting technique. So in curve fitting, what we do, we find a surface in a multi-dimensional space that provides the best fit to the training data. So we try to put it in multi-dimensional space. When I say best fit, of course, it should be in some statistical sense. And RBF, that is radial basis function, is an example that is hidden neurons forming an arbitrary basis for the input patterns when they are expanded into the hidden space. These bases are called radial basis functions. When I say basis, if you remember, probably, of course, Fourier series you might have done. So in Fourier series, you can say that your sine and cosines are working as a basis function. Also, I talked about the basis vectors in the introductory linear algebra module. I was talking about the basis function or basis vectors using which you can span the space. So this is what. So here all this the hidden part is they form nothing but a basis function. So before we
Excuse me,
go,
sir.
yeah, please.
So can you please elaborate on the third point for curve fitting?
Can you elaborate on?
The third point for curve fitting.
So if I talk about this, if you remember that when I say basis function, so basis functions basically when you talk about this basis vectors. So basis vectors, you are trying to span the space in terms of basis vector. So span the space here, what we are trying to say, you can just correlate with something like that. Something in Fourier series, if you remember that Fourier series, if your waveform is either of the form cosine, sine, or a square wave, or a sawtooth wave, or a rhombus, or it could be anything. So those are nothing but describing certain functions. You want to know what is that particular function is. That waveform may be irregular in shape, but if it satisfies the criteria, that particular function should be periodic and of finite energy. If that is the case, then any function you can represent only in terms of sine and cosines using Fourier series concept. Is that okay? Fourier series, do you remember?
Sir, I
Hello?
actually never used it.
Huh?
I never used it.
You have this course on communication theory, right?
Yeah, we did, but it was like very basic, to be honest.
Okay, okay. Anyway, then if you don't know the basis, then it's a futile exercise from my side to tell you what you mean by basis function. So we'll see that in terms of ultimately what you do that in terms of basis function, you are trying to approximate the function which is unknown to you. As simple as that.
Okay,
So
sir.
more.
Thank you.
Oh, is it okay?
Yes, sir.
Now, but then before that, before going for radial basis function and all, first we should know what do you mean by radial function itself. So radial function is a function defined in Euclidean space of Rn. When I say Euclidean space means the distance you are taking from one particular point to another point always in Euclidean in nature. That is square root of this and the square of those particular terms, whose value at each point depends only on the distance between that point and the origin. So that functions are called radial, and radial in the sense that if you square both on side, is just like a x square plus y square equal to r square. So it's basically some sort of a circular radius kind of thing can be done. So that's why they call it the radial function. And because square root is there, so because it's of Euclidean space. Euclidean space. Now, then there is something called a radial basis function. Basis function, you know, that is a basis function. So if you remember that in a linear algebra class also, I was talking about this, that spanning a space in terms of basis vectors is nothing but, and I give example also, because if you are constructing a house, and house may be rectangular, maybe square, maybe oval, maybe circular, maybe rhombus, or any shape it may be, but the brick size, brick dimension, whether you have a oval bricks for the old structure of the house, do you get it? Hello, have you seen that? Or if you want structure to be elliptical, do you get the bricks in elliptical size? Hello.
No, sir.
No. So the basis on which or any structure is formed, basically your brick dimension remains same. So based on that only they do some cutting, all those stuff, and they finally form the structure of your design of or the requirement. Sorry. So that brick you can consider as a basis. And likewise, when you have a function using which you can create another functions, and that is called a basis function. Now, if that particular function has some particular property that is a function defined in a Euclidean space, then you call that particular function as a radial basis function. And that's what is mentioned here. It says that a radial basis function is a real valued function whose value depends only on the distance from the origin, so that when you say phi of x is nothing but phi of Euclidean norm of x, means from the origin whatever the distance is in Euclidean norm sense, or alternatively on the distance from some point which is called a center, so that phi xc is phi x minus c. Okay? So any function that satisfies the property phi x equal to phi x is called a radial function. Even this is also a radial function, but there is some center. So when you have any function which satisfies this property, we call radial function. Okay. Now, one thing I just told you that there is one clear advantage of using radial basis function network as compared to the MLP. MLP is also just one of the technique for supervised training of neural network, and RBFN is another technique that is also for the supervised training of neural network. MLP uses the stochastic approximation approach, RBFN uses curve fitting approach. But apart from that, there is one clear advantage of RBFN over MLP is that the structure is very simple. In case of MLP, you can have multi-layer networks and each layer will have multiple neurons. But a RBFN is always a three-layer structure. If you exclude the input layer, then it's only two-layer structure always. One is input layer, so that is anyway not part of any neurons. You can, but still you can count it. And there is only one hidden layer and one output layer. That's all. So this is the basic structure of a RBFN. And here you can see that in everywhere in the hidden layer, whatever the system is there, they uses a basis function, which is here is indicated by a Gaussian in nature, Gaussian function. So the basis function which we'll emphasize in this particular module will be using a Gaussian function as a basis function. And why is it so? That we'll talk about. And the advantage here is that, so one advantage is the simplified structure. But of course, we'll see that whether it really learns the kind of a deep neural network learns, because you think that, okay, man, if this is the fine, then why people are going for deep networks? Are they mad or so? And then why can't they use simple this RBFN of three structure only? So of course, this RBFN has got its own limitation, because if you want a deeper structure to be extracted or the system to be learned for that, so that it may not be very efficient. But if you have of same complexity what MLP does, RBFN could do much faster than that, and you don't have to worry about so many parameter calculation here. So we'll see one by one. So there is one beautiful theorem, what is called Cover's theorem. And Cover's theorem of separability of patterns are there, and it's not a new thing. It's way back this TM Cover proposed this idea way back in '65, and this got published in IEEE Translation Electronic Computers. So what this idea is all about? So it's simple to say that the theorem says that a complex pattern classification problem cast in a high-dimensional space non-linearly is more likely to be linearly separable than in a low-dimensional space. Now, in order to explain this, actually, if we were in class, so I could have demonstrated with some real human beings as a sample data points and do that. But let me take you to the board and try my level best to explain this theorem. This is very beautiful theorem, and you'll be surprised its power. So let's say we have here. So let me use this blue, and how should I say? Okay. I don't know whether it's possible to visualize it this way, but I'll explain what I'm doing. Now imagine these are the three blue chalks I am putting in vertical position, maybe in collinear or a little bit here and there, their part. And and before that, let's say I must be having some distance here, and I'm putting here one white chalk, let's say. White chalk. Now, when you see from the front, is it possible to apply a linear boundary here to separate the blue chalk from the white chalk?
No, sir.
Yes or no?
No, sir.
No. Okay. Now, if I ask you to see from the top, can you make out the difference? Is it possible to draw a straight line or a linear line so that the two data points are separate, blue and white?
Yes, sir.
Yes. If you see from this side, it is possible to separate the two data points?
Yes.
Yes. At the same time, here also if you do, and suppose from the bottom you do. So something, what I'm trying to say is something when I just see in the towards the page, I mean 2D I'm talking about in front, it seems that they are no linear classifiable, no linearly arranged, and I cannot apply linear classifier. But when I add extra dimension, third dimension I go, if I'm able to see from the top or from the side, I can see that it is nothing but now it's possible for me to view and visualize that I can draw a straight line or a boundary so that to get linearly separable. So what you are doing that you are getting extra dimension, high dimensional space. Now I go back to the this theorem, and then because of this visualization and what I'm trying to read this theorem, try to understand that it says that a complex pattern classification problem. When they say complex, it's by default means some sort of no linear classification. It maybe comes in a very complex, different complex. Some are simply non-linear, some are very complicated way. This one. So a complex pattern classification problem cast in a high dimensional space non-linearly. Like if the problem is that if you are able to map into a high dimensional space non-linearly, then it is more likely to be linearly separable than in a no dimensional space. And this is exactly what was happening. The diagram which I have shown, that in 2-dimensional, if I see in the page, I feel that they are no linearly separable. If I go for extra high dimension, then I'm able to see very clearly possible that yes, it is linearly separable. This is the simple fundamental idea about the covers theorem. So is that okay?
Yes, sir.
Yeah. Now with this understanding, we'll go next and try to understand this covers theorem. So basic idea is that no linearly maps point in the input space to a hidden space that is a higher dimension than the input space. Now, when I see this higher dimension than the input space means what? For example, suppose your example 1, each input attributes only see 5 dimension, means 5 parameters are there. And that if I am trying to map into a high dimension means more than 5, it could be anything, 6, 7, 10, whatever it may be. If that, then you're saying that after that there is a chance that, and very much likely that, you can use a simple linear classifier to separate the two. So once the proper mapping is done, simple algorithms can be used to find a separating hyperplane, as simple as it LMS, you can say that. So this was the basic idea, and we'll see this. But before this, let's try to understand something called phi. So here we call it this phi separability of patterns. So I'm trying to develop a theory about this phi separability. Here phi is nothing but the basis function. Particularly we are talking about the radial basis function. First of all, you know now what do you mean by radial function. Now, and if I'm using as to construct or approximate some other function, so that we call a radial basis function. And I'm talking about this phi separability of patterns. So patterns are given. So what is the condition for phi separability? So suppose there are this capital N number of examples are there, or input patterns are there. Basically some sort of training examples are there in M0 dimensional space. M0 no significance, I could have written this M0 M only, but I need M1 to use, so that's why I'm using M0. Means whatever my data is there in crude form, that is a dimensionality of this. So that is M0. M0 could be equal to phi in our toy example, which we have been referring every now and then for a rent prediction system in Manipal. There is number of bedroom, number of washroom, walking distance from the college, garden is there or not, etc., etc. So let's say that is n zero dimensional, whatever is that each vector is that much dimension, and there are totally capital N number of data points are there. Now the input belongs to two classes, either C1 or C2. They form a dichotomy, and the dichotomy is separable with respect to a family of surfaces if a surface exists in the family that separates the points in class C1 from class C2. So how it is going to separate? Let's see. Now for each data point from the set entire X, we define an M1 vector phi I X I equal to 1 to M1. Now I is varying from 1 to M1. So what does it really mean to say that each data point is mapped to some M1 data points? But now remember this, M1, the value of M1 is higher as compared to M0. Ultimately, what it translates into, it says that whatever the dimensionality of X is there, that was M0. Now using this kind of map, you don't have dimensionality of M0 anymore. Rather, you have M1 dimensionality. Then the question comes, how is it possible? What we do over this? Nothing. It's very simple. So let me take you to here. So let's say that you have a simple, let me say x1, you have this x1, x2, x3. So basically it's basic three-dimensional data. Now you have defined this some phi x here, let's say, and these are the symbols which first of all talking about this in some particular function f, another is f2, another is f3. I don't know the internal structure of this one, and sorry, f4, f5. Let's see. So now here f, if I'm calling this as a whatever the x is, if I'm writing x, so here f1, whatever the structure may be, this x will pass through it and it will behave. All these things will change as per the f1 requirement. For example, let's say I'm just giving a crude idea that f1 could be x1, x2, x3 only. f2 could be x1 plus x2 plus x3, or f3 could be say x1 square plus x2 square plus x3 square. Let's say likewise you can say. So let's not bother about all these things for the time being. Of course, it's a basis function, so all will be same, but with a different centers and all. And like that you have f2x, f3x, f4x, and f5x. So whatever this is there, so now you can say that x has got dimensionality 3, whereas 5x is also a vector only, but it has got dimensionality 5. Is that okay? In a very simple, crude way, how we are going to map from this input space to high dimension space. Hello?
Yes, sir.
Okay, so if that is okay, so we'll proceed. So this is just a, I was giving a very crude idea, means how, what do you mean by that? Now, once we have this, so basically M naught dimensional space to hidden space, M1 is dimensional of the space called a hidden space, and the space spanned by this function is called a hidden space or feature space, using that if you are doing this. So a dichotomy is phi separable, means using phi we can separate it if there exists an M1 dimensional vector W such that WT phi x, if I take inner product of this is greater than 0. If that happens, then I may call it that x, that it belongs to C1. I could have used any definition of that. There's no hard and fast rule. It's up to you to decide how it is going to happen. So it's up to you, and accordingly, what convention you want, you can take it. And if that value is less than 0, then you can have this, say that it belongs to C2. And to know the hyperplane separating boundary, you always equate WT phi x equal to 0. So it is not WT x equal to 0 anymore, because it is no linearly transformed. Low linearly transformed. How do I know that it's no linear transformation? Because phi is of no linear nature. Each phi will be of no linear nature. So whatever we apply, that also gets mapped to no linearly. So this kind of separability we'll be calling as a phi separability of patterns. So we'll see on this. So we'll visit this Covers theorem once again. I'll see some of this things here. So given a set X of n inputs picked from the input space independently, and suppose all possible dichotomies of X are equiprobable. Let's say they are equiprobable. So then there is something, let's P of n comma m1 is indicating the probability that a particular dichotomy picked at random is phi separable, where class of surface has m1 degree of freedom. Where the class of surface has m1 degree of freedom means there are m1 number of variables which has to be found, as simple as that. So these things, I am not going into derivation of this. If any one of you are interested in the derivation of this, from where it came, you are most welcome to refer to the Covers papers from 65. So this is how this particular probability will be calculated. And this, you know, that's here, this is nothing but this binomial coefficient, which is calculated by this one. Now this the three popular example of this phi separable dichotomies are something like this. You may be having something which you can linearly separate without much problem. So you can have linearly separable dichotomies, Or you can have something like this. A data point is there which is from one particular class which is surrounded by the another class. So in this case, linear will not happen, and just in conventional linear or other geometry also will not happen. Only the spherical separable dichotomy will be very helpful. Now suppose you have something like this. Data points are like this and they are arranged in this fashion, let's say. Then you have quadratically separable dichotomies over there. So these are the three possible dichotomies. The question is whether these are the only thing. No, these are the elementary or rudimentary dichotomies. There may be complex dichotomies, may be also possible, which may be combination of these three. That is also possible. So now we'll try to understand this Gauss theorem. We'll go for its interpretation. So separability depends on particular dichotomy, either it's a linear, spherical, or quadratically separated, and the distribution of patterns in the input space, that is obvious. Now it says that probability NM1 states that the probability of being phi separable is equivalent to the cumulative binomial distribution corresponding to the probability that n minus 1 flips of a fair coin will result into m1 minus 1 of your heads. So simply say that if that is basically phi separable, so the cumulative binomial distribution will correspond to this particular thing. Now in sum, or when in summary, we can say that this cover theorems has got two basic ingredients. First is we have to go for no linear mapping of input space to the hidden space, and that is by x. So how many hidden spaces are required, that base decided by you. So those many this what to say radial basis functions are required. Now high dimensionality of hidden space compared to the input space, it will be always that if you are mapping to the same space, same dimensionality, that is 5 to 5, then there is no fun. It may still remain in those things, little stretch here and there, scalability, but you won't be able to make it a linearly separable. So at least if it is not much higher, so the higher dimensional space or the hidden space of yours should be at least one dimension extra than that. So that you saw that example which I put it on board. From the two dimensional, we are not able to see. Just by adding one extra dimension, we could see very clearly that is linearly separable. And one important corollary has been taken from this, that a maximum of, if you are mapping to M1 dimension, so a maximum of two M1 patterns can be linearly separated by a hidden space of dimensionality M1. So this you have to remember. Now, so before this, let's take a quiz now and see that. It's a very simple quiz. So you'll have just 2 minutes time for this. Just a minute. Wait a minute. Do this. Just okay. Just open the form. And many of you have raised the issue of connectivity or some other problem. So see, my hands are tight, and if you have missed due to any of the reason, either health or whatever may be the reason, so there is nothing something I can do. But institute might have already anticipated how to address those kind of issues. So as and when something comes, we'll address those things. And definitely, if nothing comes, I'll take into account. And uh, on my side, if things will happen, then I'll go for the oral exam for you face to face at the end of the semester for those people who missed it. And remember, oral will be more difficult than this because I'll follow a onion model. So just a minute. Just a minute. Okay, so here I go. Take 3 minute time, not much. It's very simple problem. Very simple.
So we can't see the link.
Uh, has it come now on your message? Is it visible now?
Yeah, it's visible now.
Yeah, please do. Yes, quickly do it. 1 more minute left. Yes, time's up. Okay, so we'll resume now. Okay. Yeah. So this is about the Covers theorem interpretability. We have seen all these things. Now this XOR problem is there. So before this, I'll just give me a minute. I'll just come. I'll come within 2 minutes. Just wait. I have just called. Yeah, we'll start now. So we know now what do you mean by XOR problem. So XOR problem, which we saw using MLP technique for, and then we saw that okay, XOR problem is a symbolic non-linear classification problem, and we can use MLP to solve this particular problem as well. Now we'll try to see this XOR problem and try to understand whether this radial basis functions are able to solve this XOR problem or not. So for that, and we'll take this uh, two radial functions, and phi1 and phi2. So I'm not going to extend that, and let's say only it is a two variable system. So four combinations was possible, and this one, and we are taking the centers as those data points which has got a Hamming weight of zero Hamming weight. So zero Hamming weight means we know that what's the difference between, we say take a XOR of those points and find the number of ones. So basically these ones are there and zero, they have got the zero Hamming weight. So how to find a Hamming weight, that you know. Now based on this, first let's try to understand and calculate these values, how it will be calculated. So let me take you to this one, calculation. Yeah, I got bored of setting this. So anyway, xt minus, I don't know whether I have. So we have 5 and 5 to for 4 inputs points we need to. So how do I get this? So let's take this, let's go to the board. And here we have this, just take this. Situation now first. By 1 x, and the first would be so minus x minus t1 square, and we are saying this this is the center. So this is basically example of, because here Euclidean norms are given here, so this is nothing but it's some sort of a radial function, and here it is given to us, it is 1 1, and let's say another phi 2 x. And by seeing the nature of this function, you can see that it's basically Gaussian radial function. Radial due to Euclidean norm, Gaussian because of square, and exponential of course, minus t2 square, and t2 is 0 0. If you have this one, so four possible values are there. We'll write something like this. So this is our input pattern, and then we have value of hidden space, first one, and second hidden space, same thing, this one. And let me just, so this is basically talking about this one. So four combinations possible, 1 1, we have 0 1, and we have 0 0, and then we have 1 0, right? Now let's see this, how do I compute this? So let me talk about first one here. So I'm computing it, I'll do few and then I'll show the value directly. 1 1, the first point I'm taking, or if I'm considering this is x1, this is x2, this is x3, this is x4. So let me say 5 x1. So but that nomenclature will be unnecessarily confusing, so I'll just go like this. So it's basically exp minus, and now you know that this is basically square is there. If I'm writing here, if it is x minus t1, This meaning is that if this is two-dimensional, this is two-dimensional, x1 minus t1 square plus x2 minus t2 square and square root of that. But because square is here already due to the Euclidean, this one Gaussian function, so this part will not be there. This will not be there. Okay. So based on this, so I can say this, my x values are 1 and 1. This value is 1 and 1. So I can say this entire part 1 minus 1 square plus 1 minus 1 square. So this comes out to be how much? This is nothing but exp minus 0. And this comes out to be 1, right? Now let me say about x2. And likewise, I can compute for pi 2 for this 1 point, where we said this exp minus, so I can say 1 minus 0 square plus 1 minus 0 square. From where this 0 I got? The center of the other radial basis function, that is 0, 0, that is the center. So basically it comes out to be exp minus 2, right? Exp minus 2, how much value comes out to be? Can anyone of you tell me how much, what is the value? I have to just calculate. Let me see how much value comes out to be. So it's 0.1353. Okay, so 0.1353. Likewise, we'll be calculating the values for phi 1, phi 2 for each. So I can just write here that when this combination was there, this value is 1. And for this combination, same value in phi 2 dimension, it is 0.1353. Likewise, you'll be able to fill it up. So you can see this value comes out to be 0.3678. This value also 0.3678. You can calculate using the same process which I've explained. And this is 0, so 0.1353 and 1, and this will be 0.3678 and 0.3678. Now what you have done this, whatever the values of this combination are there, just your project to do this, even though you have not added any extra dimension to it, but it has got certain beauty, and that you will see now. So that beauty thing is there. Once you have this value, just try to plot it not in terms of x, it's phi 1 versus phi 2 or phi 2 versus phi 1. So once we plot this, so this phi 2 versus phi 1 versus phi 2, you see that the value corresponds to 0.0000 is basically here. Phi 1 is 0.1353, so 0.1353, and it is phi 2 was 1, so 1, so 0, 0. Likewise for 0.11, phi 1 was 1, so here, and phi 2 was 0.1353, that is in the y direction, so it is here. So this was the point line. And for other values, either 0.0, 1 or 1, 0, it was lying here, that is 0.3678, 0.3678, like this. Now once you project this, don't you see some beauty here? Just by mapping this to using this Gaussian function, man, you have transformed a non-linear separable problem into a linear separable problem. It's very simple now, because this all, yeah, this is something which you have transformed. This after mapping it, it looks very simple. And you know that why is it so interesting to us? Because 0, 0, you know, the x, as per the XOR, the value will remain 0. For 1, 1, the value will remain 0. So all these points above the decision boundary has got label 0, whereas all the data points below the decision boundary has got label 1. XOR of 0, 1 is 1, XOR of 1, 0 is 1. So a very clear decision boundary. So this is the beauty of this function, and that's why this is something very amazing, which is much simpler as compared to the MLP. In MLP, you need at least 3 neurons to do the job. Here, you don't have to worry about just hidden space you do. And after that, linear transformation will happen. Apply a linear function, it will find the boundary. That's all. So this is the first motivational example that will exhibit the beauty of radial basis function network over the MLP. But I'm not trying to demean this MLP in any way, but I'm saying for this, of course, MLP will be beautiful, but certain aspects, you can say RBF is more elegant and beautiful as compared to the MLP. So XOR problem is one of the example, you can see that. So with Gaussian hidden functions, here we have used Gaussian function as a radial basis function. The input becomes linearly separable. Simple. So here normally RBF and learning happens in this way. You have the 3-layer structure where the input, and here there is something wrong here in this diagram wherever I taken from. There is no weights. Here there will be no weights. Actually, weights will be here only. So that we'll see how it can be done. So RBF learning problem boils down to 2 tasks basically. How to determine the parameter associated with the radial function in the hidden layer, that we'll see. That is, how do I know the centers of the Gaussian? Because in this case, we have handpicked T1, T2. You can check yourself what will happen to the XOR problem if you, instead of taking T1, T2, 1, 0 and 0, 0, you take 0, 1 and 1, 0. See yourself whether you are still able to separate it linearly or is there any problem. So you can see that. So you have to determine this parameter, means the center for the radial function. Second point is how to train the hidden to the output way. How to train this part, hidden layer to the output layer, that we'll see now. So first of all, we'll try to project RBF as an interpolation problem. So as per the Curves theorem, a nonlinear mapping is used to transform a nonlinearly separable classification problem into a linearly separable one. This is basically Curves theorem says that. In similar ways, we can also say that a nonlinear mapping to transform a difficult nonlinear filtering problem to a easier one, that is linear filtering. So this is quite a good idea. Oh man, somebody is having nonlinear filtering problem is there. He's applying some sort of nonlinear mapping, and that becomes a simple linear filtering problem. It's beautiful. So some idea from pattern recognition can be applied in signal processing as well. Now let's see this. So this is once again the same thing. So for that we have to consider that RBFN can be considered as a function map, S, some sort of function map, from m dimensional to 1 dimension. But finally, what you're boiling down, either it may be classification or regression problem, but dimension will be only 1. Either it will tell you the class or it will tell you the value if you are using for the regression. Map S can be thought of as some sort of hypersurface gamma, which belongs to m0 plus 1. That is limited. At least when you see that hypersurface, if it is not very high dimension, but at least it should be a dimension 1 higher than the input space dimension, and that is the hypersurface we are talking about, which we don't know what is that. Now, this surface gamma is a multidimensional plot of output as a function of input. When you say multidimensional plot of output as a function input, is nothing but it's a process which will projecting your low dimensional data into higher dimensional, which I gave the example using F1, F2, F5, etc. Now, practically, what is this gamma is unknown. We don't know what is the particular multidimensional plot will look like. And training data is contaminated with noise. When I say noise, means here some missing data will be there, some redundancy will be there, something of that sort. Now, training and generation phase of gamma involves few things. It is having training, so it will try to fit the hypersurface gamma to the training data point. So how we'll do this? We'll try to look it from an interpolation perspective. Then it will be very clear to you that how do I fit a hypersurface gamma which is unknown to us to the training data. And then generalization. You know that once the training is done, generalization is basically just interpolation interpolation between the data points along the reconstructed surface gamma. Means if you once you have the function known to you and other values there, you can always interpolate. Interpolate means some sort of extension, you can do that. So all these things led us to the theory of something what is called multivariate interpolation in high dimensional space. So before I'm going for multivariate interpolation, but before that, do you remember this interpolation from the first year? How do you used to do it? Does anyone of you remember? How do you do interpolation? Yes or no?
No, sir.
Okay, so we'll try to understand now. So before that, we'll try to understand there's something called interpolation problem in strict sense. So when I say interpolation problem, so what is happening that a data point is given to you, and data point is given to you in this particular fashion. So let me take you to the board. So you have something like this. Let's say my training data is given to us, and this is of the form, say, xi di, such that I is varying from 1 to n whatever, and xi, each xi is say some m dimensional, and each gi is say one dimensional. Okay, so this is my training data. So what you're trying to understand that in this data you want to know that what is this particular function in this particular block, so that when I give this xi, it produces the corresponding di. You want to know this particular function, right? For that, so literally what you do, the interpolation in strict sense is nothing but interpolation. You're trying to find this particular f. What is that? So here, interpolation in strict sense, just whenever, suppose you have found this value of f, then this value of f should be such that if I take any one from the training and plug it here, it should tell me the corresponding di value which is known to me from the training data itself. It should be that exact. So finding this f is basically the interpolation problem. You can say that the function. So you can say that you are doing here function approximation only, but here we are using the idea of interpolation, which is not very different from what we have been doing in the neural network, but that we are doing using same different process. We use weights, etc. So with this, let me go to the definition of this interpolation in strict sense. So we are saying is that, let's say, given a set of n different points, x and I is varying from 1 to n different points are there. Each xi is of m0 dimension, and a corresponding set of n real numbers, that is the desired output corresponding to each xi, is di, which is one dimension, let's say. Now we are required to find a function f such that m not to r1. This function is that taking m input attributes and produces one output. And this satisfies the interpolation condition. If it satisfies the interpolation condition, that is, when I give this xi as an input to this particular function, I should get the value output di, and it should happen for all. So this kind of problem, interpolation problem, is called problem in strict sense. Most of the time this does not meet the requirement. If this happens, means you have not approximated, rather you exactly find the function which is describing this particular training data. Okay, so this is basically what is called interpolation problem in strict sense. Now for strict interpolation, the interpolating surface, that is the function f, is constrained to pass through all the training data. Means all the training data has to pass through, means you have to substitute and do all those things. Now radial basis function technique consists of choosing a function f. Means now here you are saying that in RBFN we are choosing this particular function in this particular form. In this form, there is a phi, that is a radial basis function, which is projecting data xi to the higher dimension, and after that it is the weight corresponding to the hidden space to the output layer, and sum of all these things are equal to 1 to n, this which you are approximating using, that's what we are calling as a f of x. Now here this phi I and this particular part, and there are n basically is a set of n functions and known as a radial basis function, right? So we'll see that, can I do something? Can I correlate this with this? Can I do something? So we'll look into this. So known data points xi are taken to be the centers of RPF. Now here we have taken each named data points of the training data as a centers of the RBF. So it means these are centers that is mentioned from here also. Now, so I can write this particular equation, this is equation 3, that for x, if I write like this, so instead of writing x, can I do xj? If xj, I can write here xj, that's all. So if I do this, I can write xj minus xi, something of this form. I can do that. Now, in this particular equation, if I plug this relation, that is 2, that is fxi equal to di. What I mean to say, if I say xj here, I should get equal to dj value. That is the meaning out of it. If I plug that to those things, I can write this. Whether this point is clear to you from where this dj is coming out to be?
Yes, sir.
Okay, good. Thank you. Now, this I'm rewriting this dj, and further we may write, and this is for one instance only, just for one instance. So we can write something like this. So for example, for x1, so then we will start expanding this particular form. So where this j is equal to 1. So I is varying from 1 to n anyway. So phi 1, w1 phi x minus x1 etc. w2 etc. x1 will remain fixed dn, and that is equal to corresponding value du. Similarly, I can substitute instead of j1, now it is j equal to 2. When it's j equal to 2, so you have something like this. Likewise, I can do this until j is equal to n. That is the nth data point. Once you do this, you get dn. Now this entire system of equation, can we write it in some sort of matrix form? Hello? Is it possible to write it in some matrix form? Can we do so? Yes or no?
Yes, sir.
Okay. So we can simplify this by one simple notation, that each xj minus xi of this particular function, we just write phi gi. That's all. If that is the case, we can simplify this process and we can write something like this: f11, f12, sorry, phi11, phi12, etc. And in this particular fashion, we can write it in the matrix form, where phi gi is defined by this, and this I have mentioned. Once you have this entire thing matrix form, we can represent and we can consider this entire one as a d vector and w as this particular as a vector, and including an entire this capital phi. So this is, and call it in this phi will be calling as an interpolation matrix. Now this entire system of equation in the matrix form can be written as phi w equal to d. Now we were supposed to find w only, that is the weight, so in the output layer. That will basically help us to find the linear boundary between the points so that it becomes linearly separable. And that's why it will help us to transform a complex non-linearly separable into a linearly separable problem. Okay. So phi we don't have to worry, you can just find it out. W we can write it here. So D, so phi inverse D, phi can go over there and inverse. Now there is a problem. Problem means we have to choose function phi in such a way that this entire matrix phi becomes a basically positive semi-definite or positive definite. Means it should be non-singular. Means its inverse should exist. Who is this? Okay, nice song, man. किसे बुला रहे हो भाई? Okay. So now this the question comes is that phi is non-singular. So how to ensure that the phi is a non-singular? Because we otherwise, if it is not non-singular, then you cannot find a weight for the output layer, that is from the hidden space to the output space. So weight is not fine. If the weight you have not find, then you have not find the decision boundary. Equation of decision boundary is not known to you, then problem you are not able to solve. As simple as that. So we have to find some ways which will ensure that phi is non-singular. So we'll see now. So non-singularity of phi is guaranteed by Tom Micheli basically. So Micheli's theorem, and Micheli's theorem simply says that. So nothing very high-fi, very simple steps is talk about. Let xi1 to n, these n data points, be distinct points in Rm0. Means all the data points in your data sets are distinct. They are not redundant or not replicated. Distinct. If data points are distinct, then your n cross n interpolation matrix phi, whatever you'll be getting it will be non-singular, and it is guaranteed fact, and it has been proven and checked, right? So this is one way to do this. Now, of course, we'll see some other aspects of this Michaelis theorem as well. Now, when this M1, that is your the number of dimension in the hidden space is less as compared to the total number of data points, then we can find W that minimizes this error weight. We can find. So error weight equal to n fxi, which will be getting from minus di, because fxi exactly it won't be there. So the actual value fxi minus di, some sort of error will be there. The square of this we have to minimize, and but we know that fxi is wk phi kx. This we also know. But when we have this k equal to 1 to m1 sparing. Now solution involves, of course, I'm not solving here. Though it is straightforward, you can do and substitute this. You can transform this particular equation in some sort in a vectorial notation. Even this also could be in vectorial notation and work accordingly. And this solution involves pseudo inverse of psi. Pseudo inverse of psi, we know that when it cannot be guaranteed that your psi is a square matrix, then you don't have the conventional inverse, rather you have pseudo inverse. So this pseudo inverse, if you remember, I already talked about in linear algebra. What do you mean by pseudo inverse? So here particularly pseudo inverse of phi, so phi t phi minus 1, that is the inverse of this phi t t, that is pseudo inverse, and phi is of course n cross m1 matrix. Now when we see this, so Michaelis, when he gave this theorem that if the data points are distinct, then the resulting interpolation matrix is guaranteed to be singular. So based on that particular framework, people have found out many other forms of interest for the RBFN. So one of them is multi-quadrics. So multi-quadric is of this form, that is phi r equal to r square plus c square over basically square root of those things. As c is greater than 0, r is in real value, and there is something called inverse multi-quadrics. So in multi-quadrics, this is defined by this one, and another is a Gaussian function. For this particular module, we'll be particularly focusing on Gaussian, and I want to tell you here, by looking at this function, you can say that inverse multi-quadrics and Gaussian functions are localized in nature. When I say localized in nature, what I literally mean to say that phi r approaches to 0 as r approaches to infinity, either for inverse multi-quadric or for the Gaussian function. But same cannot be said about the multi-quadrics. It cannot be assured that it will reach to 0 when r is to infinity. No, it basically some sort of a non-linear way of increment is here. So these two things will always let you, we will always give you non-singular phi interpolation matrix, but this may be a singular, or it will be a function which will not be invertible, or you can see it may be a singular function, so you cannot find it directly. Now radial function networks comes here. So this I want to talk about this a little about, and then there are certain design settings, so that we'll talk in the next class. So why I said that the other diagram is wrong, because I don't know, I didn't notice while copying it from somewhere. Between the input space and hidden space, there is no concept of weights. No concept of weights. Weights comes into picture only between the hidden space and the output space. Remember that. So otherwise, two sets of weight we need to calculate, but it is not so. It is not so. So here we have this particular diagram, radial basis function network, and so we have, let's say, input layer is there, some m input points are there, means one particular input data set with m dimensionality, and then we have hidden layers m1 equal to n. So we are considering that. Now you can imagine the problem now. The number of points or the basis points used in the hidden space is equal to the number of data points in the training data. M1 equal to n. That is the case. So each unit is described by this particular point. Now output layer M2 is always 1. It does not have any other dimension. It's just only 1 point. Either may be classification problems with a small label, or a specific regression problem, then it's a value. That's all. But M2 can be anything, but M2 is always less as compared to M1. This is always true like that. Now we'll see all those things. So now onwards, but in this particular problem, as I told you earlier also, we'll be focusing on this Gaussian function as a radial basis function. Remember that if this Euclidean norm symbol is not there, it's just a plain Gaussian function, right? Plain Gaussian function. But instead of that, it is Euclidean norm is there. So it's basically the function is used in a radial sense, which basically is a Gaussian radial function, not conventional one. So formulation of RBFN Y interpolation is neat in this case. Training samples is typically noisy, but use of interpolation based on noisy data could lead to misleading results basically. Now we need a different approach for design of RBFN. And here you can see that there is a redundancy of neurons in the hidden layer by virtue of the redundancy of that may be inherent in the training sample. In the training samples, of course, if there is a redundancy, suppose that if the data point 1 is replicated 3 times. So same thing, nothing new is happening, but as far as this data structure, this structure architecture is concerned, you need to have three more neurons in the hidden layer, which is not a good idea at all. So we'll see. So first of all, the limitation is that suppose you have, and that's why you can understand also the limitation of this, why we can go for deeper network, not this one. There is a problem here. If I have some 10,000 or 20,000 data for training data points, I need to have 10,000 neurons in the hidden space. It is not a good idea. And it is, if the data is training data is redundant, there's a further problem. So we'll see the limitation in all these things in probably the next class. So I'll stop here. Okay. So just be there and let me